We begin our journey into linear models by looking at the case where there is just one explanatory variable. And this is called simple linear regression. So the name simple refers to the fact that there's just one explanatory variable to distinguish it from the case that we'll be working towards, which is where there are multiple explanatory variables. Okay, so simple is just the naming convention for this case. Okay, so specifically, we're looking at a linear model. And so since there's just one predictor, you have a response and one predictor. So let's denote it as follows. So we have a response variable y, going to our usual notation, and one explanatory variable x. Okay, so since there's just one of these variables, we don't need to use subscripts in simple linear case. Okay, and so what does the model state? So we conceptualize the model so that the response y is modeled by this expression, so beta 0 plus beta 1 x. Okay, so this part looks familiar to us as the equation of a line with intercept beta 0 and slope beta 1. So we're saying that the relationship between y and x can be described by a straight line. And to account for the fact that the line generally will not perfectly explain the relationship between x and y, we incorporate the error term epsilon. Okay, so therefore, we view y as described by the equation of a straight line plus some random noise. Okay, so for our data, in practice, we have to fit this line using a data set. And so what does our data look like in this case? Well, it's going to consist of pairs, so you're going to have x and y pairs. So we'll denote them as follows. So data consists of pairs xi, yi. Let's say we have n of these pairs, so I goes from 1 to n. So we have n data points. Okay, so before we do any model fitting, as we probably learned in our first stats class, is to plot the data before we do anything else. So in this case, we have a pair x and y, and so the natural tool to visualize this data is scatter plot. Okay, so we can make a scatter plot for these xy pairs. I'm going to go over here, use this graph that I've set up, do so. I'm going to label here my x-axis and my y-axis. And each pair xi, yi will be a point on this plot. So I'm just going to put some points on here. Okay, so that would be an example of a scatter plot. Okay, so it's a useful visual tool because it allows us to visually assess whether there's potentially a relationship between the x and y variables. And in particular, we can often see visually whether a linear relationship, specifically, is appropriate for the data. Okay, so I'll say over here, the scatter plot allows us to visualize the relationship between the two variables. So we can visualize if there is a relationship. In this case, we're specifically looking at linear relationship between the two variables. Okay, so that's our visual tool in this case, and I also want to connect this simple linear regression case to a concept we saw when we first learned probability, and that's the notion of correlation. So let's first remind ourselves what is correlation. So we can make a scatter plot, and we also consider the correlation as a quantitative measure for the relationship between two variables x and y. Okay, so back to the definition. If x and y are random variables, then the correlation is defined with this formula. So we have the usual notation for correlation is correlation coefficient, rho. So that's the correlation between x and y. And so this is computed by taking the covariance between x and y and dividing it by the standard deviations of the two variables, standard deviation x and standard deviation y. So you can think of correlation as a normalized version of covariance because it divides through by the two standard deviations, and we can show actually that this correlation coefficients ends up being between -1 and 1 as a result. Okay, so this is the formula we learned in probability when x and y are random variables. In this case, we don't have random variables for x. We're going to treat x's as constants in the regression, but nonetheless, we're going to have data consisting of pairs in x and y. So we can still calculate the sample correlation from our paired data. Okay, so based on the data, so this is the xi, yi's, we can compute the sample correlation, and how to do that is simply to replace these covariances and standard deviations by the corresponding sample estimates. So we can estimate okay, so I'll go up here. Okay, so this is the sample correlation. Okay, so we'll call this, denote this by R, because that's the sample correlation computed from data. Okay, so what we do is we replace each of these by the sample estimate. So for the covariance, we use 1 over n minus 1. And then we sum the cross term xi minus x bar, yi minus y bar. So to remind you, when we write x bar, that refers to the sample mean. So it's the average of all the n x values, and then the same thing for y bar. Okay, and then we also need the sample estimates of the standard deviations. Okay, so we call that standard deviation is the square root of variance, and so we can write the square root. So we'll put in a square root, and then we'll put the sample variance of the n x values. So that's 1 over n minus 1, and then summation xi minus x bar squared, and then we do the same thing for y. Okay, so this expression simplifies a little bit, so we can cancel out an n minus 1 from the top and bottom. Okay, so then we are left with this top part, which is the product of the x term and the y terms, and on the bottom we have the square roots of this sum of square term involving x, and then a sum of square term involving the y's. Okay, and so as we'll see as we progress in this course, these sorts of expressions, so taking the each of these x's and subtracting the mean, and then these sorts of sums appear quite often. So we will define a shorthand for these expressions. Okay, so I'll do that in blue here. So this part on the top is a sum involving a cross between x and y, and so we will denote this as s sub x y. Okay, and then on the bottom here, so following the same logic, this part you can actually think of as xi minus x bar times itself. Okay, so we can use follow similar logic to come up with a shorthand. So this sum of square on the bottom I will denote as with the subscript double x, and then for this one we'll similarly denote s with a double y subscript. So using this shorthand then, the correlation can be expressed as the s subscript xy, and then on the bottom we have the square root of these two sum of square terms. So we have s sub double x and then s double y. Okay, so that's our sample correlation coefficient, which we can calculate on the basis of n pairs of x and y values. Okay, so let's remind ourselves of the interpretation. Okay, so what does correlation measure? Okay, so correlation measures the strength and direction of the linear relationship between two variables. Okay, so let's put this down here. So it measures strength and direction of the linear relationship between two variables. Okay, and I want to emphasize here the word linear because correlation picks up linear relationship, but not necessarily any relationship between x and y. So x and y could be related, maybe quadratically or some other way, and correlation will not necessarily pick that up. Okay, but in this case, since we're working with linear models, there's a strong relationship between the correlation and also the goodness of the linear model in terms of fitting the data. So the two things will be well connected in this case. All right, so the correlation coefficient and the way it's estimated based on the data, so R here, has interpretations. So first thing to note is that the correlation coefficient is going to be a value between minus 1 and 1. And so that can be shown using Cauchy-Schwarz inequality, but we won't go into the details here. So suffice to say, we will we'll state these facts. So the correlation coefficient will be between minus 1 and 1, and this is the interpretation. So if the absolute value of the correlation, so if it's either positive and close to 1 or negative and close to minus 1, so this is what we consider a large correlation in absolute value. This refers to that x and y would have a strong linear relationship. And then when the correlation is close to 0, then we would say that there is a lack of a linear relationship. Okay, so you can see therefore the magnitude of the correlation refers to the strength of the linear relationship. On the other hand, there's also direction, and so this is where the sign of the correlation coefficient comes into play. So when the correlation coefficient is positive, we say there's a positive linear relationship, and then when r is less than 0, then we have a negative linear relationship. Okay, so in this plot here, we see that as x increases, y also tends to increase. So the correlation here would be positive, right? The slope of the line that relates x and y would be positive. So what we can see here is the correlation tells us that when r is 0, that as y increases x, y increases as x increases, but it doesn't tell us how we can predict the value of y from x. Okay, so let's also note that, but r is not sufficient to help us predict y from x. Okay, so in particular, we need to estimate the slope in order to do so. So we need the equation of the line to be able to actually make predictions, although correlation measures the strength and direction of the linear relationship. Okay, so let's go here then, and let me continue this alligator example with an indication here of what these points might refer to give you a concrete example. So alligators are of course quite heavy, and according to Wikipedia, male adult alligators could be as heavy as 360 kilos as adults. And you might imagine that the weight of an alligator is probably associated with some measurements that you can take of it that are easier to take. So you can imagine predicting the weight of an alligator from some measurement that's easier to take. So I'm going to choose one here. So this was a study done in Florida, not surprisingly. And so researchers measured as an x variable what's called the snout to vent length. Okay, so in this diagram of the alligator, that's the distance from the tip of the nose to right behind the head. So this is the snout to vent length. Okay, so let's label this on here. So that typically ranges from about 80 centimeters to about 180 centimeters. Okay, so this is SBL in centimeters. And on the y-axis, we'll have the weight of the alligator, which ranges up to about 360 kilos. So this is the mass. In kilograms. Okay, so in this case, we can see that the correlation is positive. So our next step then is to actually ask, well, okay, we based on the visuals and maybe based on the correlation, we get some sense of the relationship between x and y. Okay, so now let's actually fit the line. Okay, so let me then write down the model for the case where we have n pairs of data points, x and y. Okay, so continuing that, we have for data xi and yi. So let's say we have n data points. So the model for these data points would be to take that line, and then we build a model that relates each yi to its corresponding xi. Okay, so we write it as follows. So yi equals beta 0 plus beta 1 xi plus epsilon I. Now, I'll point out here that in terms of notation, you notice that I use both capital Yi and also lowercase yi. So there is a purpose for doing so. When I write capital Y, I'm talking about it as a random variable. Okay, so when we talk about the actual observed data values, then I will use lowercase yi. So when we're talking about the model, we're talking about yi as a random variable, and therefore capital yi. Okay, so we can handle these multiple data points by adding a subscript to refer to the ith data point. And so our assumption then is that this this random noise term is normally distributed. So let's write that assumption down. So epsilon I is distributed normal 0. So again, normal, mean 0, variance sigma squared. Okay, and in this case, we're going to assume that all the epsilons have the same distribution and they're all independent. And so the acronym is IID, which I'll put on top of the tilde sign. And so when I do that, it means that all of these epsilons are independent. So that's the first I, independent and identically distributed. Okay, so of course in practice, when we actually fit data, we will need to verify, or at least be willing to check that this is indeed a reasonable assumption for our data. Okay, so we will get to that later on in our course. Okay, so under this assumption, if epsilon I is ID, normal is 0 sigma squared, what does that tell us about the distribution of random variable yi? So using what we talked about in terms of the properties of the normal distribution, we see that yi is a constant, so beta 0 is beta 1 xi, and then epsilon I is the random variable here. So together, that means yi is also normally distributed, and the mean is beta 0 plus beta 1 xi, and the variance is sigma squared. Okay, so over here, this part, so beta 0 plus beta 1 xi is the mean of yi. And so to capture that idea, we can use the notation mu I. So that's the mean, defined to be the mean of the ith data response variable. And then this part, sigma squared, is the variance of yi. Okay, so in particular, notice we're assuming that all of the yi's have the same random error variance. Okay, so I would also point out here that yi's here are independent as a result, but not identically distributed. Okay, so they're independent because we're assuming that all the epsilons are independent. Okay, so therefore all the yi's are independent, but they're not identically distributed because they can have a different mean. And in fact, the mean we're assuming is the equation of our regression line. Okay, so on average, y will be distributed at the line that we fit to the data. Okay, so now we're ready to talk about, well, how do we actually estimate values for, in this case, the two unknown parameters, the intercept beta 0 and the slope beta 1. And so the method that we'll focus on is called least squares. Okay, so we'll do what's called least squares estimation, which I'll abbreviate by LS. Okay, so I'll give you the intuition as follows. Okay, so first we start with the observed response value, so that's yi. And intuitively, we want to fit a line such that the observed values for y are going to be close to the line that we fit. Okay, so the equation of the line that we're fitting for yi has mean beta 0 plus beta 1x. So we want y to be close to that. So I'm going to subtract off beta 0 plus beta 1 xi. Okay, so that is the difference between the actual value and what the line is going to predict and fit for that value. Okay, and so we want intuitively we want these differences to be small, but these differences can be both positive and negative. So suppose we square it. So we square the difference. So now this is a positive number, and the farther away yi is from the line, the bigger this square will be. Okay, and then we have n data points, so we sum this quantity over the n data points. And then the objective is to minimize this as a function of the two parameters, beta 0 and beta 1. And that's what we call the least squares approach to estimation. Okay, so the natural question here is, well, why square, right? So there are other ways that you could use to quantify the difference between the value and the line. For example, why not absolute value? And indeed, this is not the only way to fit parameters beta 0 and beta 1. Okay, so if you put absolute value, it would be least absolute deviation, right? So that would be a different objective function. But one of the reasons why least square is often used is because it has a nice connection to method of maximum likelihood estimation. So in fact, when in the case that we're considering, which is that the errors are independent, IID normal, 0 sigma squared. In fact, this least squares solution is equivalent to the maximum likelihood estimator, and we know that the MLE has good statistical properties. And so this connects why least squares is a common approach, and in fact, it is equivalent to the MLE when in the normal case, which we are considering. So I just make a note here. This is equivalent to the MLE when the epsilon i's are IID normal. Okay, so sometimes, like if the epsilon i's, for example, were a different distribution, or maybe the epsilon i's were correlated and not independent, then least squares would not be the same as the MLE. As you notice that the least squares expression doesn't actually use any information in itself of what the errors epsilon I has as its distribution. Okay, but in the case where the errors are normal, then the two are equivalent. Okay, so our goal then is to calculate these values beta 0 and beta 1. And so let's treat this thing as our objective function. So let's call this S as a function of beta 0 and beta 1. Okay, so this is where we need to bring out our calculus and use the techniques of calculus to minimize this function. So what we need to do is take partial derivatives. Okay, so in this case, when we have a convex function, in fact, when we set the partial derivatives to 0, we get exactly the solution we are looking for, and those are the values of beta 0, beta 1 that minimize this expression. Okay, so we will take this s function and take a derivative with respect to beta 0. Okay, so we do our calculus, apply the chain rule to this. Okay, so we'll do 2, and here it's clear that the summation is from 1 to n, so I'm going to drop the index of the summation. Okay, so inside we have yi minus beta 0 plus beta 1 xi, and take the derivative of the inside. So that's just going to be minus 1. And do the same for the second equation. So again, chain rule. Okay, and now I'm taking respect to beta 1, and so the coefficient on there is going to be minus xi. Okay, and so those are derivatives. Okay, so let me just pause here. So this s function is referring to this objective, and we've taken its partial derivatives. Okay, so next step is to set these derivatives to 0. So set partial with respect to beta 0 to 0, and partial with respect to beta 1 to 0. Simultaneously, and then solve for, and then we will solve these equations to get the critical points for beta 0 and beta 1, because the function is convex. In fact, that gives us the minimum that we're looking for. Okay, so let's work on the first one. So let's set this equation to 0, so partial s with respect to beta 0. So gives us, so setting this one equals to 0 is equivalent to saying that this is 0. I'll just drop the constant and then apply the summations. So we have summation yi minus, okay, and that's summing beta 0 n times, so we have n beta 0, and then we're summing beta 1 times xi. And so we can pull out the beta 1 summation xi. Okay, so I've carried the summation through the entire expression, and then I can set that to 0. And so from here I can solve beta 0 in terms of everything else. Okay, so I'll move n beta 0 over there, and then to the right side, and divide by n. Okay, so when I do that, so I'm going to have summation yi divided by n, and that's actually just the definition of the sample mean of y. Summation yi divided by n, so I can replace that with y bar. And then similarly, when I take beta 1 times summation x and divide by n, that gives me beta 1 x bar. Okay, so the first equation gives us beta 0 in terms of beta 1, and then also y bar and x bar. Okay, so with that in mind, we can now work on the second equation. And since both of them are satisfied simultaneously, we can simply plug in what we found for beta 0 in terms of beta 1, and then solve the resulting equation. Okay, so we have derivative with respect to beta 1, that's set to be 0, so that implies then that we have, so again dropping the constant, so we have xi, and then inside we have yi, and minus, so now I'm going to plug in this value for beta 0, so I will have minus y bar and then plus beta 1 x bar. And then I will have minus beta 1 x I. Okay, so all of that is equal to 0 after plugging in beta 0 into the second equation. And so I can do a little bit of factoring here. So I'll group the terms like this. Okay, so I'll have xi yi minus y bar, and I can pull a minus sign and along with beta 1, so that inside the summation is xi times xi minus x bar. Okay, so that so I pull a minus, so then it has this symmetry, so it's xi minus x bar and then yi minus y bar. Okay, so all that is 0, and so from here we see that we can solve for beta 1 by rearranging. So beta 1 is to take summation xi yi minus y bar and divide it by this term next to the beta 1, summation xi minus x bar. Okay, and so these provide the solutions for beta 0 and beta 1. The only other thing I'd point out here is this expression is actually equivalent, and we can show this using properties of summation, that we can write this as xi minus x bar, so I can put in a minus x bar here. And then I can do the same thing for the bottom, so xi minus x bar, and so this becomes a squared term. Okay, and so this is the more familiar form because it involves, again, something that looks like the covariance between x and y, and then on the bottom we now have a sum of squares for the involving the x terms. Okay, so these two are mathematically equivalent. Okay, so there we have it. Those are the solutions to the minimization, least squares minimization problem. Okay, so notationally then, how do we denote the estimate? So we introduced the notation that uses hats. Okay, so when we're writing down the model, we have these fixed but unknown constants, okay, parameters, beta 0 and beta 1. And so after we estimate them from data, we denote these estimates, so to notationally distinguish the estimates from the unknown, true unknown parameters, we put hats on the estimates. Okay, so we denote estimates using a hat on top. So we put beta 0 hat and beta 1 hat as the estimates computed from data, which are these two expressions. Okay, so in conclusion, then, the line that we are fitting to the data has an estimated slope and estimated y-intercept beta 0 and estimated slope beta 1 hat from these two expressions. So beta 0 hat is y bar minus beta 1 hat x bar, and beta 1 hat, the slope estimate, is this expression. Okay, so we have now used our data to determine what's the so-called line of best fit that goes through the data. So on average, the line is a correct predictor for the data, but it doesn't fit perfectly, so there will be error around the line. So to capture that concept, we'll define two other things. So the first is the fitted value. So we call, okay, so remember I denoted mu I to be the expectation for the ith data point. So now that we have fitted the line, we have the fitted value. So that again, we'll put a hat on top of it. So this is the fitted value of y for the ith data point. So this is simply the evaluating the equation of the line we just fitted at the point xi. So beta 0 hat plus beta 1 at xi. So we call this the fitted values. Okay, so I'm going to use this plot to demonstrate. Okay, so suppose we fit a line through these points. Okay, so let's add what reasonably looks would be a line. So this line would be represented by what we just calculated. So the equation of this line would be beta 0 hat plus beta 1 hat x would be the equation of this line, and so that's our line of best fit. Okay, so relative to that, then we have the data points from which we fitted the line. Okay, so let's look at a particular one. Okay, so here is a point. Let's call this one xi, yi. Okay, so that means down here is xi and here's yi. Okay, and so this point here, okay, so the value of the line at this red point would represent, so the y value of that would represent this fitted value. It's the value of the line at xi with the intercept and slope that we have fitted. So this one here is mu I hat. Okay, so as we see, the line does not fit all the data perfectly. There is variability in the points around the line, and so we have this difference. We have the difference between the actual value observed, yi, and the fitted value from our simple linear regression model. So this difference is what we call the residual. And so we'll use the notation E for the residual calculated on the actual data. Okay, so this distinguishes it from epsilon I, which is the random variable form. So this is the actual residual from the data for the ith data point. So we take the actual observed value of the response variable yi, and then we subtract the fitted value mu I hat. Okay, so this is called the residual. So on this plot, then the difference between yi and mu I hat is this distance from the red to the green point, and so this distance is the residual E I. Okay, so there we have it. That's how we conceptualize this simple linear regression case. So just two variables, a response and one predictor, one explanatory variable. And so this is how we develop the tool of least squares estimation to get these estimates for beta 0 and beta 1, which provide the line of best fit through our sample of n data points. So we'll pick up on this on Monday.